So let us solve one numerical problem based on pulse code modulation, and the problem states that in a PCM system, if the code word length is increased from 6 to 8 bits, the signal to quantization noise ratio improves by the factor. So the question asks, if we increase, if our encoder encodes the code word by 8 bits, then it will improve the SQNR, right, signal to quantization noise ratio. So what would be the, if this is a signal to quantization noise ratio, or you can also represent it by this signal to noise ratio. When we use 6 bits is 1, if the signal to quantization noise ratio for the first scenario when we use 6 bits to represent our code word is 1, signal to noise ratio S by NQ 1, and when we use 8 bits we represent the signal to noise ratio by S by NQ 2, then what is the factor by which our SNR improves? So the question asks this K. We want to find out what is the value of K. So as you know, the PCM does this, it samples the signal, then quantizes the signal, and then it encodes, right? So if you remember that signal to quantization noise ratio of a PCM system is signal power, average signal power divided by noise power, that is del square by 12, as there is no change in the message signal. So average signal power will be same, but since now you are encoding using 8 bits, so we improve the efficiency, because we remember that our n number of bits is nothing but log 2 of L, where L are number of levels, number of quantization levels. So as number of quantization level increases, the accuracy increases because the quantization error decreases. So in the first scenario wherein we used 6 bits to represent our signal, number of levels were 2 to the power 6, and when our PCM uses 8 bits in order to represent the same signal, the number of levels would be 2 to the power 8. And if you remember that our delta or the quantization interval was 2 MP by L. So for the first scenario, our delta 1 is 2 MP by L1, and for the second scenario it will be 2 MP by L2. So signal to quantization noise ratio, as you can see, is proportional to 1 upon del square. So for the second scenario, signal to noise ratio divided by signal to noise ratio for the first scenario will be del 1 square divided by del 2 square, correct? So it will be L2 square divided by L1 square. Since the peak value will be same, and here we have to write L2 as we just missed the slides, I think. So L2 was 2 to the power 8 and L1 was 2 to the power 6. So 2 to the power 8 is square into 2 to the power 6 is square. This is nothing but power 16. So signal to quantization noise ratio for the second scheme, second scenario is 16 times the signal to noise ratio for the first scheme. So the answer of our question is 16.